Okay, so regarding modular arithmetic, it's nice mathematics, and it's a nice uh, notation that Gauss invented for this. But what's the use? What's the point? And it turns out actually that this is something where mathematicians often brag for whatever reason. I think this is kind of silly, but mathematicians often brag about how sometimes their work is just so pure that it hasn't found an application. Mathematicians have never, ever found any bit of math that hasn't been useful eventually. And so maybe there's some modern day math that isn't exactly useful yet, but historically, if you go back, everything that every mathematician has ever done has been useful somewhere. That's a slight, uh, that's a dramatic claim, but that's not far from the truth. If it's not exactly true, it's not far from the truth. Number theory is no different. So this modular arithmetic is actually the basis for modern cryptography and is therefore the basis for every time you use your credit card online, something about modular arithmetic is happening. And if we have the time, I'd like to talk a little bit about the cryptography because it's some nice number theory. It's useful and it's interesting. So until we get there, you'll have to trust me that this stuff is actually useful in real life. That is not why it was discovered. It's just a nice fact. It's something nice about numbers that people didn't know before. And so that is basically that is what it is. But there's a good reason why these are useful. There's a second reason why why modular arithmetic is useful, and that's in that it lets you prove nice things easily. So let me explain this. What I want to do is I want to think about the following. So I'll call this a proposition. This is a proposition that's going to be in our in the online notes, but let me just rewrite it here. So I'll sketch it a little bit. But if A is congruent to B mod M, my pen decided not to work here. And if C is congruent to D mod M, then both A plus C is congruent to B plus D mod M, and AC is congruent to BD mod M. So in this sense, the congruence mod some integer m behaves like an equal sign in that you can somehow multiply both sides of this congruence, and this is true, and you can add both sides of the congruence, and that's still true. So this is a proposition. I think this is easy enough that I will leave this to you to prove. I don't remember if I think I left this as an exercise in the notes, but it's just straightforward. So if you just assume that A is congruent to B mod M and C is congruent to D mod M, that means that A is equal to B plus MK, C is equal to D plus ML, and I've already done like 80% of the proof for you. You just check that when you add them and multiply both sides that everything is fine, and it is. So that's one thing here. As a corollary, okay, so as a corollary here, if A is congruent to B mod M, then AC is congruent to BC mod M for all integers C. Okay, I might have included this in the proposition in the notes, but this is definitely true. So take any integer, you can multiply both sides of a congruence, and this is still true, even if you have 0. So if C is 0, the statement is still true. It's just not useful, but it's still true. So we can just say that it's true for all integers. And the reason for that, and the reason why I call this a corollary, is that it follows immediately from this the second conclusion of our proposition down here. And that follows because notice that C is congruent to C with respect to any modulus, so mod M for any M. And that's because the relation that we defined before was reflexive, right? M divides C minus C for all integers C. So that really is the second story here. So if you look at C is congruent to D mod M, if you replace that with C is congruent to C, then you immediately get what we want. So that's why it's a corollary. One other corollary, and this is a corollary that involves a little bit more justification, but if A is congruent to B mod M, then A to the n is congruent to B to the n mod M for all non-negative integers, n. Okay, and so this follows, basically just to give away the punchline here, this follows from induction. Okay, so I'll let you prove this in some detail, but this is a straightforward induction proof. So if A is congruent to B, then A to the n is congruent to B to the n mod M. Now, one thing that you, so just to give you an idea of an example, let's prove that 3 divides 5 to the n minus 2 to the n for all integers n, for all non-negative integers n. Okay, this is a perfectly valid number theory proof that we could talk about, and there's a few different ways that we could do this. And I think that one good way to do this is induction. So let's prove this by induction. Our base case is n equals 0. So our base case is that 3 divides 5 to the 0 minus 2 to the 0, or 3 divides 0, which is true. Everything divides 0, even 0. Okay, so 3 divides 0, which is true. For the inductive step, here we need to be a little tricky. For the inductive step, what we're going to do is we're going to assume that 3 divides 5 to the k minus 2 to the k for some k greater than or equal to 0. And then we want to show, that 3 divides 5 to the k plus 1 minus 2 to the k plus 1 for that k. So, yeah, we just need to get to work. If 3 divides 5 to the k minus 2 to the k, then there exists some integer L. So there exists some integer L where 5 to the k minus 2 to the k is equal to 3L. Hence, we need to be a little bit tricky here, but 5 to the k plus 1 minus 2 to the k plus 1 is equal to 5 times 5 to the k minus 2 times 2 to the k. And then I'm going to write 5 as 2 plus 3, which basically comes out of nowhere, but it's a trick that works. So if I write 5 as 2 plus 3, then I can distribute that amongst the 5 to the k. So this is 2 times 5 to the k plus 3 times 5 to the k minus 2 times 2 to the k. And what happens is this is going to be 2 times 5 to the k minus 2 to the k plus 3 times 5 to the k. And the point is that 5 to the k minus 2 to the k is a multiple of 3. This is 2 times 3L. And 3 times 5 to the k is a multiple of 3, because there's a 3 in there that you can factor out. So this is 3 times 2L plus 5 to the k. And therefore, 5 to the k plus 1 minus 2 to the k plus 1 is a multiple of 3. And that proves it by induction. So therefore, 3 divides 5 to the k plus 1 minus 2 to the k plus 1. Okay, and so that's enough to prove, remember what we were proving is that 3 divides 5 to the n minus 2 to the n for all integers n. Perfectly valid proof. This is one where I'm also going to give 2 proofs. When you see the second proof, you're going to laugh. Proof 2. 5 is congruent to 2 mod 3. Right, because 3 divides 5 minus 2. In fact, 5 minus 2 is 3, but 3 divides 5 minus 2. Hence, 5 to the n is congruent to 2 to the n mod 3. Because that's what the above proposition said. Let's just go back up and look at it. If A is congruent to B, then A to the n is congruent to B to the n for all n. And again, that corollary follows by induction. but here it is. So 5 is congruent to 2, therefore 5 to the n is congruent to 2 to the n, and we're done. That's the end of the proof. It's literally a one-line proof. You can put a little box there. Okay, so that's the kind of thing that modular arithmetic will do for us, is it makes these statements almost trivially true, right? Super easy to check, very nice. Okay, so this is one thing that it's going to be really good for.